Hi everyone, and thanks for joining. My name is Lucian. I've had quite some experience with ML in the past 10 years or so. I had my first touch with ML in the first year of university. I had the pleasure to be in an internship at Bitdefender in the ML research team. And then at that point, I started reading some ML books and kind of getting the grasp of it. And I continued doing things like that. I have worked mainly in startups. I worked in a startup that was building a chat assistant before ChatGPT. Then I was a co-founder at a startup which was building medical research. So like image recognition. Actually, it was about detecting tumors in CT scans. So tumors and organs at risk. So like delineating the liver or the heart or the lymph nodes, stuff like that. And now I have started my own startup, which is a little bit hard to explain, but it's more in the foundational ML side. So the goal would be to build a vast network, so like a very big network of micro agents which collaborate and work things out collectively and kind of but much deeper than what you see in agent world today. That's a little bit about myself. About today. Today is the title I chose for this workshop is ML Intuition, because I wanted to give you a little bit of an intuition of what happens in ML at the foundational level. So starting from the basic operations to like how a model learns, the way I view it, which might be different from some other schools of thought, let's say. And as a general guideline for today, I prepared for you a little website, a little web app, which I'm going to give you the link right now. So we'll start with a little bit of an introduction of like an alternative way in which you can see the whole ML process and how these magic networks learn from data sets. Then I prepared for you three little games, so to speak, which go from like the smallest level to the largest level. So like from the basic operation in which the neural networks live and thrive by, right? And then going a little bit further up into exploring one layer of a neural network, and then kind of exploring and visualizing a whole neural network and what it does. If you want, you can also check out the link in the chat. So the link should basically go to the same page, so everybody in this chat can also check the whole material, and we can go through it together. So let's start. So the first thing that I wanted to give you is sort of a little bit of an alternative intuition into how we frame this ML perspective. So first of all, the ML game, the way I like to call it, is you are given some points, some like data of a hidden function, which is this data set, and then your task is to bring so like to extend this function so that you can provide a prediction, what we're saying here. So you have a prerequisite, so like an existing database, an existing evidence of, I don't know, cat photos or texts that are spam or whatever. And then at query time, at inference time, you are given another point, another example, and you want to either classify it or give it a number that's representative. So it's basically like taking these data points and extending this domain of the data set that you have to like the full domain of axis. So in case of photos, you have some like, I don't know, 1,000, 10,000 photos of cats and non-cats, and you want to extend it to the whole range of photos so that you can predict cats for all the photos in the world. That's sort of the general idea. So it's like a mapping problem. And if you think about it, this in itself provides some challenges. Like how can you pretend to put a label to a newly assigned data point which you know nothing about? Like what's the criteria here? And I think I think an intuitively good way to think about it is to consider for this new data point that I don't know how it is, how similar it is to some data that I have already seen. And the idea is that, I don't know, I have a photo. I don't know if it's a cat or it's not a cat, but it looks very similar to this other photo that I have in my training data set that's actually a cat. So I'll just say it's a cat at that point. So this is the main idea behind these kernel methods and these kernel machines, so to speak. And the whole idea boils down to this function. And if you understand this function, then you probably understand a lot of machine learning. And I'm going to break down a little bit of this function because it's not as hard as it may look. So what this function says is that what I'm going to predict for the new data point x, which is this f hat of x, is just going to be a sum of the labels that I have in my data set. So kind of I'm going to get an average of the labels of the data set, but the way I average them is I don't do just like the whole average. It has to depend on what I've seen and how similar it is to what I already know. So this k of x and xi, you can think of it as like how similar these two are. Or rather, I think a better way to think about it is how relevant is the data point xi in order to get in order to decide the value that we're going to assign of x. So like if you think about this, the bigger this value is, the more influence point I will have on the output, and the actual influence is going to be in the label of it. So like basically the bigger this value is, the more similar this data point is, ergo the more influence its label is going to have in the actual output of the function. And this doesn't look like training neural networks. This sounds like old research, but I'm telling you, there's like a lot of new and interesting research exploring this, and it's actually the fact that it's proven that every ML model, every neural network is kind of doing something of this. It's like this plus memorizing, so like compressing this data set that we have into some model, but virtually doing something like this. So it's like keeping track of all the training data and just mapping a point in terms of similarity. But like the big challenge is, in the real world, things don't look that easy. So like this example is a pretty simple example, but kind of illustrates my point. So if you think about a picture of a dog in the sun and a picture of a dog at night, if you look at the pixel of those pictures, so like the raw signals that these photos expose to the model, to the neural network, those pixel distributions and those pixels are really very different. However, the concepts are really related. So the big trick is how can we compute this good similarity representation between two inputs, two photos in this sense. And not only that, but like it's very task dependent as well, because two pictures that are very similar in terms of predicting whether a dog is in the pictures or not might not be as similar if our task is to predict the time of day where that photo was taken. And neural networks, in a nutshell, what they do is they kind of take this space of photos and they warp this space and they fold this space. So if you think about it in like the pixel space, a dog at night and the dog at day are kind of like very distant points. What these neural networks do is they kind of fold the space until these concepts actually overlap. So like imagine you're taking a sheet of paper and you're just folding and then folding and then folding, and at some point after many such folds, all the dog pictures end up pretty close in this stack of paper layers that you have, and and there you go. Now you've kind of merged these together. So we're creating these sort of wormholes that kind of take distant objects in space or distant points and kind of teleport them together. And that's what we're going to be exploring in this workshop. So right now, let's go to the first exercise and talk about, I'm calling it the touch. So like the most, let's say, the bread and butter of neural networks. And the and butter of neural networks are these vectors. What are vectors? I mean, some say they're like arrows in multidimensional space. Some say they're like points. Some say they're planes. I will just call them a list of numbers. So they're like a list of numbers. Each number says something about this data point. And the bread and butter, the way these vectors exchange information between one another, or the way they interact, is via this magic formula, or this magic thing, which is called the inner product. This is the formula of the inner product between two vectors. You probably have seen it if you've had some like past experience with ML, but this is the dot product between two vectors. And this dot product sort of answers the question how similar these two vectors are. In reality, it's much more than that. It's like dot product can have so many definitions that it's pretty hard to enumerate all of them. Why? Because vectors in themselves, if you think about representing them, you can think about representing them as arrows. I don't like this representation very much, but we can think of them as arrows. So like the dot product kind of encapsulates how aligned these two arrows are, so how much they're pointing in the right direction. But that's not only it, because vectors are not only arrows. They can also be looked at as planes or hyperplanes. So if let's do it 2D. So you can think of a vector as an arrow, but you can also think of it as sort of this plane, this line that's perpendicular to that arrow. And I don't know if you have had this sort of definition, but like an alternative definition or an alternative way in which you can think of the dot product, you can think of it as like the distance between a point and the plane of the encoded by the other point. So it's also sort of like a distance measure. It's also like an alignment measure. And I think in order to understand sort of like the rawest things of ML, you can kind of think of both definitions and sort of mix between the two. But also you can think of this definition like this vector inner product between two vectors as sort of an overlap. And I think this also makes sense in some way. So if you think about if vectors are like DNAs of the data points or DNA or a pattern, you can think of the dot product as being how much this pattern matches this data point. So like if you think of one number being, I don't know, some features, has whiskers, some other number being has ears pointy, right? If you want to match the template of a cat with these vectors, you're probably going to be increasing the confidence that it's a cat if it has whiskers. So like there's like a positive influence of that feature towards the answer, and also for like having pointy ears, but maybe a negative difference. So if you see a human hand, right? So like if the image has a human hand, maybe it's, I don't know, like humans with whiskers and pointy ears. I mean, neural networks have a difficulty in categorizing those as non-cats anyway. So I don't know. So back to it. So like the rules of the game are like this. If you have a highly positive score, you can think of the vectors as being similar, right? If you have a 0 score, we call that orthogonal. It kind of means that they share nothing with each other. So they're like from different planes. If you have a highly negative score, you can think of them as being the exact opposite of one another. And for this game, let's play a little game. So the game here is you have this vector v, which you can see it in here, and you have this vector w, and using these sliders you can modify the values of w. And in this lower area, you can see like the strength of the similarity, so of the dot product. So you can see like if for example I have 0.81 and I modify this to be higher, then this value would be higher. What I want you to do with this exercise is maybe for 5 minutes just explore, have a little bit of fun with it. You can change this from a dot product to the dot product after we apply a hidden matrix. I want you to also kind of look into that and see sort of how it differs inside your expectations. And you also have this button, which you can think of it as a hard mode button, where the W vector is constrained so that its norm would be 1. What we call this thing is it's sort of on this sphere. If you've ever encountered this sort of term. So sort of like once I increase one of the dimensions, you can see that I cannot just take all of them as being the max. So the others will need to adjust so that they're lower in order to account for the magnitude in change. And what you can do is you can try to maximize it through these different things and see how it works. If you want to enable the normal this button that does this hard mode or not, that's up to you. If you want to use this matrix to see how it differs, it's up to you. But like for 5 minutes, try to be a neural network and see if you can achieve your target value here. So the target value can be, I don't know, maybe biggest to the right, as big to the right as possible, or as big to the left as possible, or maybe try to make it exactly 0 and see what it takes, like how you do it. And then maybe in about 5 minutes, let's discuss together. Great. So we've got a question. I will say what's written in the chat so that people that are going to be watching afterwards also know what's going on. So a question was, what's the maximum possible value of the inner product of V and W in this app? And it should be the when the bar is full. So like but don't try to overfit on like making it full, but think of it as like the fuller the bar is, the closer you are to. Good question. So a question was, shouldn't it happen when each individual vectors are close to each other? You'd think about it, you'd think that would be the case, but in fact, if you think about the formula, so definitely, like if you unclick this normalization, there's some interesting thing that you can notice, right? I'm hoping you've had enough time. Otherwise, I'm going to be spoiling some facts. But does any actually beforehand? Does any one of you want to share any interesting thing that they might that they found, or like something that's maybe weird from like what you've experienced it? First of all, who experienced with like choosing the dot product and the matrix and kind of trying to do both exercises? I don't know if you can raise your hand or something like that. But like the first interesting fact the first interesting intuition that you can give from here is like, if you tried to maximize this dot product, you would see that like if I go up and down on this one, it will just increase if I go upper, right? So like if you look at how the bar behaves, it virtually tells us that I mean, this one, it doesn't do anything, right? But that's because the V4, so like the thing we're multiplying, it has weight 0, so it doesn't matter. So I can bring it up and down, and hopefully you noticed that this doesn't change, and hopefully you realize that it's because this value is 0 here. But like if I want to maximize this, I would just go sort of like this. So like this is the maximum value, and you'll see that all of these sliders, all of these knobs are either the lowest at their lowest point or at their highest point. And that's obvious, right? Because like if you want to maximize the sum, the weighted sum, where these are the weights, whenever a weight is positive, you want to make this thing as large as possible. Whenever the weight is negative, you want to make this as small as possible. But like if you try to look at this one, which is basically a hidden matrix that's being multiplied before doing this dot product, you'll see that it's not really dependent on how you take these values, but sort of works like if you kind of force yourself to not look at the v values, and you just look at these sliders, which is basically what machine learning models do, you realize that it kind of works the same. So kind of I go in the direction in which this one increases, and like everyone just goes at that point. Of course, like if you click on this normalize, it's going to be completely different, because sort of what happens now is this normalization kind of forces that the sum of squares of each values is up to one, is exactly one. So whenever I try to increase, so for example 0.81, I want to increase this, you'll see that at some point this value decreases. So it's not like I can take all of them. Like it's not like I can take the full value for this, because this makes the other values go exactly to zero. And kind of in this interesting norm, like if you look at it, the like I can just how can I say, I can take a little bit off from the maximum, from 1, from W2, which is like 0.06, but all of these other things get increased by a lot more. This is because like the norm is kind of forcing the sum of squares. So like by giving away a little bit from like doing this greedy thing of taking the largest weight and just cramming this volume bar up as much as possible, I can actually make space for a lot more of this weight. So just to answer your question, and the question was, shouldn't it happen when each individual W and V are close to each other? It's sort of like that, but it's like that whenever this W is sort of normalized. So when you don't have these unlimited resources that you can allocate to W, if this makes sense. And maybe another thing that's really interesting, if you wanted to make this zero instead of full, you maybe noticed that it's really easy. It's much easier to make it zero rather than to make it all the way to the left and all the way to the right. Any idea why that might be the case? So feel free to write in the chat if you have any idea why it's so much easier to get zero than to get, or like to get close to zero than to get a big value. And in all cases, they compensate each other, kind of. Any other thoughts? If not, then the way I like to view it is like there's lots more ways to achieve zero than to achieve these maximums. So if you want to maximize this sort of dot product, to maximize the alignment between two vectors, you kind of have to give in your whole energy towards the direction of vector v, the one that you're trying to maximize this alignment with. But like if you want to have no alignment, so like sort of orthogonality, the way they see it, there's actually lots of ways of achieving that. You can see that like from any state that I take this, I can basically sort of cram this, and at some point, like if at this point it's 0.2, at some point it's going to be zero. So like there's much more ways to achieve close to zero. And one very weird intuition about like one very weird fact about this hyperdimensionality stuff, because like now we're working with 8 values, but neural networks are working with a million values. And it turns out that the bigger the dimensionality is, the easier it is for like the more likely it is for two vectors to be orthogonal or almost orthogonal. So like have this dot product equal to zero. In fact, if you look at the theory, if you have a highly enough dimensionality, you can prove that virtually any two random vectors will be almost orthogonal. This is counterintuitive because if you've taken a linear algebra course, you might have this notion of linear independence and the fact that there can only be d mutually independent, d mutually orthogonal vectors in a space of size d. But the thing is, like, if you allow for a little bit of error, you can cram. That's the really counterintuitive fact. If you allow a little bit of error, so like you don't want the dot product to be exactly zero, you can allow 0.01, which is almost like they don't influence one another. You can like cram exponentially many vectors. Why that's super important? Because I'd like you to think of these vectors as sort of like these features, right? The features of an image. And an image has billions of features. And the thing is, if you think of each feature as sort of a direction in this space, then you can cram so many, like billions of features into 1028 numbers and have them almost not interacting with one another. That's like the super counterintuitive fact, bonus fact for for highly dimensional geometry. And it's a really nice exercise. If you want, we can discuss later. But right now, let's go to the next step. And in this next step, which is called the fold, we're going to be going inside a two-layer neural network and see how it actually does this thing that literature, or like some may call folding the space. Like I've maybe heard, I don't know, once or twice that these neural networks fold the space, and I was really curious how they, like, in what way they fold this space. So this is a two-layer neural network, a really nice drawing. For an input, like you have two input neurons, two output neurons, and n hidden neurons. And this is the magic formula of a two-layer neural network. You can see, like, we're taking this input, we're multiplying by this weird matrix W1. We take this sort of activation function. I'm not sure how I'm not sure if you know why we're taking this activation function and not just letting it be, but that's sort of one of the aims of this exercise. And then we take another matrix and we multiply it by it. Kind of, I don't know, looks a little bit counterintuitive in the first tense. But what I want in this game to show is that actually one way you can think of it is like you can think of this as folding the space, and you can think of W1 as telling you the direction, the orientation in which the fold is going to be made. So, like, if you think about folding a paper, W1 tells you basically where you're going to be making this fold. Sigma tells you how you're going to do this fold. Like, are you going to like just make a hard crease between like in this fold of the paper, or are you going to roll this paper sort of over itself? And like, are you going to be smooth, are you going to be hard, are you going to be somewhere in between, things like that. And W2 kind of tells you how much you're going to be stretching the paper, that like the strength of the actual folding. So here I've got you. I've prepared for you a second game, and in this second game we're actually going to be building, or like visually kind of looking at how a neural network folds the space. How this works is we have these two screens, and we can choose here the activation function. So the way it works is like we can click on a point, and once we click on a point, we basically set up the first part of a neuron. And when we drag this neuron, this space, you can see like this ReLU what it makes is it kind of folds this half of the plane, right? It sort of modifies it. So it's like we keep one side of the paper fixed, and then we kind of drag along or like stretch it like an elastic the other side of the paper. And once we release, we have a neuron. You can see here the way it's sort of folding this space. But that's not so interesting about one neuron. But look what happens when we take multiple. So like if I want to add another neuron and I stretch it, you can see that this is sort of how it warps the space. You can see that like sort of this space is folded, and sometimes it just so happens that it crosses over itself and sort of brings this sort of shape. And again, what's interesting about these sort of shapes is that you can see like focus on maybe one region of the space and see that sort of there's multiple points that end up in the same region after you do this thing. So maybe one exercise is to check it, like maybe change the activation function. You can see like I can change the activation to be none. And what happens here is like I do the same thing. So it's like the same formula, it's the same model, but like I do it with no activation function. And you'll see something interesting. Basically, what happens down here is, which by the way, down here is the actual formula. So it's actually summing over all the actions that I'm doing. So like right now I have a network of 3 neurons. I can even activate or deactivate some of them. So I have 3 neurons, which I'm going to be adding a 4. You can see what happens here. Basically, I'm not doing much. Like I could have done everything with just 1 neuron, which might be surprising for you if you didn't hear about this fact that actually if you don't do any activation, not much happens. So it's just like stretching the space. Just like you can see, not much doing. But once I choose an activation function, the actual folding happens, and I can fold the space over itself and over itself again, and maybe even one more time. And again, this is one layer of a neural network over 2 input neurons and 2 output neurons. This actually happens in much bigger dimensionality, but like this is sort of what's happening in one layer of the neural network. And as a bonus, you can actually tick this one, and this is a data set. So like you have 2 blue points and 2 red points, and the task is sort of to make these. So like if I do something like this, you can see like I brought these two blue points together. So the task is sort of like, yeah, imagine these are 2 pictures of a cat, these are 2 pictures of a non-cat. You want to make the cat pictures as close to each other as possible and the non-cat pictures as far away as possible. So I mean, interact with it a little bit, try to make a little bit of an intuition. I know it's a little hard to grasp. I know the more clicks you do, the harder it will be to understand. But that's maybe something to appreciate about these neural networks. The whole complexity that arises just from a single neural network of like 2 layers. Of course, like once you add more and more and more. So like, yeah, play a little bit with it. Maybe change the activation function to sigmoid. See how this thing warps the space differently than scroll. Works a little bit differently than using the ReLU activation function. Maybe change it to GELU activation function and reset, and try to get a little bit of the grasp of it. And be a neural network for 5 minutes of your life. So we've got a comment. They are very sensible. That's like partly true. It's sort of so there's the math of it is a little bit different. It's still the same function. So it's still the same W1 plus. So like ReLU of W1 times X all times W, or like these activation functions. But the way the W1 and W2 are computed are a little bit different, so that it's it's a little bit easier for you to see some things. So first thing that you might notice is that basically with this model, with just one neuron, we can just take any point and overlap it with any other point. And sort of like if you want to make this picture in which the red dots overlap and the blue dots overlap, which is, by the way, the famous XOR pattern, you can just take and do it like this. So there's like this hidden power, which there's a whole paper about it. It's really interesting. It's called like neural networks are universal approximators, which says that a two-layer neural network can approximate basically any function. And one way to see it is like by just interacting with it and seeing kind of the power that it brings you. So you can basically take and move stuff around almost without almost with total freedom. Of course, it's not actually total freedom, but you can actually just move stuff around until it fits, right? Especially with ReLU. And this happens because in ReLU, this is like the maximum of x or zero, right? This ReLU activation function, which basically lets you keep any half of the plane just fixed, like do not touch it, and move a whole other half in sort of almost any direction that you want. So like this is the power, and that's why this works so well. Another thing that you might notice when changing this is like if you have this data set and I want to use another function, so like this sigmoid, to kind of wrap this thing around, right? First of all, it looks much different, right, than the ReLU sort of picture. But second of all, you can see like it's pretty hard. I mean, it's a lot harder than ReLU to sort of make these 4 points like one next, like the blue points to be one next to each other and the red points being one next to each other, but they being separated, which kind of tells you a story, right? I mean, there was this thing in history of AI in which first they would use these sigmoid functions, but then they would sort of migrate towards these ReLU function, and they figured out that the performance is better with ReLU function, and kind of like now we're sort of a neural network, and we kind of see that what was a lot easier with ReLU, it's much harder now. And also the patterns look a lot different. So like with sigmoid, you can kind of have an impact only on a little bit of the space and kind of roll, and it's different, right? You kind of roll it with each other instead of like roll it in a sort of small region instead of this ReLU, which sort of kind of does lots of things at the same time, right? I mean, if you think about it, this is a much bigger, like you said, they are very sensible, right? So ReLU has a lot bigger power of warping this space than sigmoid has. And maybe another thing that's really interesting is I'm going to hide the points for a little bit and show you, like do a little bit of a picture, right? And we're going to take a look at this picture. I don't know. I'll just do some weird stuff here and maybe have some more stuff here. It lags. And I don't know. Let's look at this picture for a little while. And you might notice that we're looking at a 2D picture, right? But it sort of looks 3D. Like it sort of looks like I'm taking a 3D picture and I'm kind of putting it in a 2D box, right? It sort of looks like a 3D terrain, or like it looks more high dimensional than 2D, right? And I mean, the reason why this looks like this is because it is actually higher dimensional. So like whenever the way you can think of it is whenever you have more than two neurons here, you have two input neurons and two output neurons, but you have more than two, you have 7, right? I'm going to hide some of them, and I don't know, there's four of them, but this doesn't look 2D. This looks like a 3D space with hills and valleys, and I'm kind of looking at the 2D mesh of it. It's what you're seeing, and this sort of observation is exactly right. Because if you think about what happens, it's actually transforming this 2D terrain into a multi-dimensional, and then it's projecting back into 2D. So you're kind of taking a picture of a much higher dimensional space, and once you take the picture, you operate with the points as if they were this picture, but in fact, the inner dimension of the space is much higher dimensional, and that only happens when you actually include these activations. So you kind of have to make these creases. You have to fold this space in order to expose a higher dimension. Which, I mean, after it I mean, we're looking at a 2D photo. Like, these are 2D points, but in fact it's more than a 2D image, right? It's a 3D or maybe even a multidimensional image. Yeah. So, I mean, let's go and look at the third example as well, and I don't know, maybe wrap it up, or if you have some more questions, we can allocate like 5 minutes for the question. So the third example is, I think the most interesting one. It should take a while to load. So if in the first one we looked at sort of how these interaction work at microscopic level, right? At like the basic operation, the dot product between two vectors. And the second one is looking at the layer. For the third one, we're looking at the whole network. So for this third example, we want to look at how like the impact these warps and these folds in space make for an actual example. So what I did is I took the MNIST data set, and I took 100 images from the validation set, 10 per digit. And I also took a trained network, or like I trained but it's better to say that I trained a network on MNIST. And what I wanted to see is how these, like how close to each other the pictures of the MNIST dataset look while the network is training. So this looks like a this looks like a hairy ball of some sorts. I don't want to make any more comments on it. But how I want to see how I want you to see and understand this picture is that each vertex here is an MNIST image labeled with one of the 10 digits of MNIST. And the way they will position themselves inside this space, this 3D space, right? Because we can rotate it. So the way they will position themselves is so that they will be sort of close to their neighbors. And one thing about visualizing these highly dimensional networks and these highly dimensional kernels, or that's the way they call them. But again, when we talk about the kernel, I want you to think about a compatibility function or a similarity function. These are very highly dimensional. They project them to 3D space or to 2D space and kind of look at the positions of the points. I think this all only brings half or even less than half of the image. I think the best way of visualizing this is by looking at them as a graph. So we'll imagine a graph in which the more similar two examples are, the more colored will be the edge, so like the more transparent. So you'll see in a minute how this works. But again, now we're looking at the very disorganized graph. So like everything is more or less the same correlated. Like this 7 is kind of like, I can kind of see the edge between these two sevens. So these two sevens are kind of similar in representation, but I can also see all of these white edges. So it means like pretty much in the beginning, so we're looking at the input layer of the network, and we're looking at the network at step 0 when it's not been trained. And you can see that every layer basically looks like a big mess of everything. So like more or less everything is close to everything. There's not much separation. And you'll see that this thing will change once we tune this checkpoint. So this slider, basically, when I turn this slider to the right, it means that in the beginning I'm looking at the model, the network that's not been trained. So step 0, no trained, and I turn it to the right, and it starts to be trained. So like at this point, it's been trained for 500 steps. I don't remember exactly how many examples were in one step, but the the idea is to kind of see that in this visualization, that what happens with this network in its infinite and very weird warping and folding of this space, what's going on is it kind of takes these edges and makes sure that they're as colored as possible. So like these sixes should be close to each other, while the edges between two different digits sort of get dimmed as the network gets trained. So like if we go to the end of the network, you can see that what we end up is this really interesting constellations of digits of MNIST in which like sevens are sort of close together, because this edge again is like very opaque, so it's not transparent, but like all of the edges between different digits, you can see that there's like really vague. So like what happened is like the network made this six, for example, and these two be very distant in this final logit space. But again, like we can look at how this evolves from like layer to layer, right? So at the input layer, again, this is in the image space. In the image space, things are pretty messed up. So like you cannot differentiate just from the pixels. But you can see that once the network starts pre-processing, like in this first projection, you can see like there's a lot of noise has disappeared. And when we normalize, kind of some noise gets back, and activation brings back a little more of this. But again, this is in preparation of the next layer. So kind of if we skim through the layers, you can see that it's sort of getting progressively more and more separated. So right now there's like maybe two edges which are not right. So like this 9, it says that it's pretty close to this 3, and this 3 is pretty close to the 3, and the activation kind of rescales it a little bit. So like makes this, I mean, it says to 0. I can talk a little bit about why that happens, but it might be a little bit confusing. But like the last stage actually just separates them. Yeah, another maybe interesting thing about this graph is, if you look at these like the network trained at step 10,000. Of course, when you change this layer, like some edges might appear, some edges might disappear. That's because of the internals of like how each layer operates, and like the way we're computing these transparency values. But again, like if we look at activation 1, and then we go to activation 2, and then we go to activation 3, you can see that this sort of white mess, it's getting dimmer. So like each, or maybe, I don't know, norm 1, norm 2, and norm 3. So each sort of block of this neural network is eliminating more and more of the false similarities. So it's bringing more and more closer and closer together the right values than the ones that are not right. So in a way, the neural network, what it does is it progressively brings closer together the labels. So like the examples that are all 7 or all 8 or all 9, while kind of pushing away the examples which are from different digits. That's sort of the way I wanted to think of it. But yeah, you can play with it. It's pretty interesting to play. Unfortunately, I don't have the data for other neural networks. I would have loved if I could show you some other models. This is, I think, an MLP model. Maybe a convolutional one would be interesting also, but the idea in general is the same. So sort of this warping and squishing, and I don't know, putting things on top of each other, and kind of scaling things so that they become distant, and then folding again, and all of this process sort of brings together the data that should be close together in the sense of, I don't know what your task is. I mean, that's all I have. That's all I have prepared for you. This website will be active. I mean, it will be somewhere on the internet. I don't know if it will be at this page forever, but it will be on the internet, so you can check it out at any time. But yeah, if you have any questions, or maybe any insights, anything that you found interesting or not so interesting. The question is how I made the website. I opened the Claude Code instance, and I told it, make me a website based on ML intuition. I pressed enter and waited for a couple of hours. And this is what Claude Code proposed. Thank you, and all of you for being in the audience. We have a chat message. Thank you, very nice.